Hi, my name is Jimmy Perez, and this is a presentation on the maximum strain of high-temperature, high-stress steam pipes for coal-fired power plants. So throughout this presentation, I'm going to be discussing the motivation for this study, a bit of the background material on coal-fired power plants and the areas that I'm focusing on, the objectives of this study, the geometry that's used in the study, the boundary conditions applied to that geometry, the mesh optimization process, the simulations performed on that constrained geometry, and then I'm going to talk about the simulations and the results of them. And then finally, I'll get to the concluding points. Coal-fired power plants are the most common source of energy production. To increase that energy output and the efficiency of the power plant, higher operating conditions are needed. Coming from the turbine, hotter temperatures and higher pressure combustions are needed to generate more RPMs to generate more power. Coming into the turbine from the boiler, the steam carried by the steam pipes reaches a temperature of 600 degrees Celsius and up to 13 megapascals. Here on the right, I've included a picture of a steam pipe that's ruptured due to prolonged exposure to those conditions. Understanding the behavior of how the steam pipes behave under these conditions can help us to improve the design of the power plants in the future. Computational software can help us to understand key areas of failure under realistic, high-temperature, high-stress conditions applied to realistic geometry. Understanding that behavior can help us to implement that and improve the design of actual power plants. And improving that design can help them last under these conditions for prolonged periods of time. So a bit of background on how these power plants operate. The process of the power generation is as follows. Coal-fed, combustion-heated boilers are used to convert water into high-temperature, high-pressure steam, which is fed into multi-stage steam turbines. The turbines are used to operate generators to produce power. The piping used to convey the steam from the boiler heating system to the turbines is typically some form of T91 or P91 alloy ferric steel. When operating at peak efficiency, steam temperatures reach up to 600 degrees Celsius, with turbine inlet pressures around 13 megapascals at speeds between 25 and 58 meters per second. They typically choose P91 steel for its creep-resistant properties. So the goal of the study is to better understand the effects of the conditions necessary for peak efficiency in coal-fired power plants on key components of the power generation system, namely the steam pipe inlets of the turbines. The objectives required to meet this goal are to create a realistic geometry, apply the properties of P91 steel to that geometry, and constrain it appropriately like it would be in a realistic setting. Then, to establish the appropriate loads. Using that wholly constrained and applied geometry, running a simulation to identify the limiting strain for the geometry of a typical steam pipe, and then identify the stress distribution and the likely area of failure. So I've included a picture on the far right to show you the actual component that I'm going to be modeling. And the geometry itself consists of an inner diameter circle, that's the inner diameter of the tube, of 800 millimeters in diameter, with an outer diameter of 835 millimeters. That's the thickness of the wall of the tube is going to be 35 millimeters. It's secured with a bottom portion that is 960 millimeters in diameter and 40 millimeters thick, with screw holes that are 33 millimeters in diameter, and there are 12 holes on each port, so 24 holes in total. The tube itself is swept up 1000 millimeters along the radius or along the diameter of a circle of 900 millimeters and swept vertically 1200 millimeters. And that gives us the shape of the steam inlet pipe. The properties for P91 stainless steel that I've applied to that geometry are the density of the steel is 7,800 kilograms over meters cubed. The Young's modulus is 2 e to the 11th pascals, with a Poisson's ratio of 0.29. Fixed supports are applied to each of the 12 holes on each port, and with 2 ports, that's 24 fixed supports in total. So the load on the geometry is applied in the form of pressure on the inside of the tube on all surfaces. The pressure that's applied is 13 megapascals. So in this study, I'm going to compare the results of simulation using 2 different meshes. One is the standard mesh, and this is how that looks now with 12,565 nodes and 6,082 elements. And I'll get into a bit as to why I'm using 2 different ones on the next slide. So applying a refinement to the mesh in ANSYS, I found that due to a difficulty with my license, it only allowed me to apply the refinement to a select few parts of my geometry. I couldn't apply the refined mesh to the 2 long tube sections, and the most relevant place that I was able to put it was on the curved elbow. And during the 2 simulations, that's where the stress accumulates most, but I'll get into that in a little while. But that's the most prudent place to have that refined mesh. With the refined mesh, I have 31,585 nodes with 17,536 elements. So the simulation is going to consist of the total deformation, the equivalent elastic strain, the equivalent stress, and the structural error. Total deformation to see how the geometry is going to deform, the equivalent strain to see the strain profile, equivalent stress to understand the stress profile, and the structural error to see where it's most likely to fail. So using the standard mesh, simulating with 13 megapascals from the interior, it deforms most highly on the edges of the curved elbow. That's why I would apply the refined mesh there later on. But for now, it reads with a maximum deformation of about 2.066 millimeters, which isn't a whole lot. And everywhere else seems pretty structurally sound. So the strain profile is, it's almost negligible. The only significant strain appears in the under part of the elbow with in the units of millimeter over millimeter, about 0.0040909. So it's not a whole lot of strain. It's very, very far from the rupture conditions of what P91 usually ruptures at. The stress profile, it's a very similar story here. In the units of megapascals, the limiting stress is about 645 megapascals, and that's also in that lower elbow region. And comparatively pretty low. It doesn't reach anywhere near the max of 1436 megapascals. So looking at the structural error, it seems like it would most likely fail around the edges of the ports rather than the elbow itself. Although similar structural error occurs at the under part of the elbow where the strain and stress accumulate the most. So looking at the refined mesh simulation, when looking at total deformation for that refined mesh, it gives us a more accurate depiction of where it's going to deform, although in reality it's really only like a 0.1 millimeter difference. So it's more accurate, but it's still ballpark the same. And it looks like on the edges of that elbow, it's gonna deform about 2.3 millimeters, which is a little bit more accurate than the 2.066 from the unrefined mesh. And in that case, it's more of a 0.3 millimeter difference, but it's still a very small deformation. It gives us a good ballpark, but it's just more accurate. Like with the total deformation, the results with the refined mesh are ballpark the same as they were with the unrefined. It still has the most accumulated strain in the bottom region of the elbow, where it's about anywhere from 0.003 to 0.004 millimeter over millimeter in strain, and it shows relatively the same amount of strain. Similarly, with the stress distribution for the refined mesh, the stress still accumulates in the bottom region of that elbow, where it reaches about 820 megapascals, which is well under the maximum allowed. And same story with the refined mesh's version of the structural error, where it's most likely to fail around the ports where the screw holes are attached rather than the elbow itself. So in conclusion, the limiting strain, or at least the strain that it reached under the conditions that were applied to it, was about 0.0049 millimeter over millimeter. The stress that it only reached was about 820 megapascals. The geometry of the steam pipe with the properties of P91 alloy steel is sufficient enough to withstand the applied stress at peak efficiency operation of coal-fired power plants. The study of P91 steels in power plants shows that it's fully capable of withstanding the temperature and pressure of steam inlet pipes. Again, my name is Jimmy Perez. I'm a graduate research assistant at the University of Texas at El Paso. Below is my email if you want to contact me. And thank you for taking the time to view my presentation.